Good morning, everyone. My name is Human Kazimi. I'd like to thank the organizing committee for the opportunity. The title of the talk today is Radiative Wireless Power Transmission for Satellite Applications. The outline of the talk is focused on the space needs for wireless power transmission modalities. And this leads to a variety of concepts of operation, such as microwave wireless propulsion for launching various rockets and satellites to space, and then once in space is space-to-space standoff power feed from one point to another, and also a later discussion about the geocentric orbit transfer as the various satellites transfer to a variety of orbits and move within space. Then further on, we'll talk about the energy requirements of for space applications, what type of energy, the amount of energy that is required for some of these applications, and then lead into the technologies such as the directed energy sources and receivers that could allow that to come to reality, and what further technologies that need to be developed for that, and then follow with a conclusion. So this is a chart from NASA. As you can see, it's a journey to Mars and what is actually required to enable this journey from Earth to Mars. You can see science, exploration, and technology are the themes for this. And the idea here is you can't possibly launch everything from Earth and take it to Mars and then build within Mars. At some point you have to have, as they could call it, waypoints or stations that need to have manufacturing capability built into them, and also have systems that are can function for a long time in space and build themselves to enable longer journeys and more hardware and software, obviously, to be built in space for those desired applications. And these things could include anything from orbiters, landers, and also in space habitats that will be part of all of that. And as mentioned, you know, the space launch systems itself, where you can launch from space, yet another capability that might be of very, very important use. In the meantime, the commercial cargo and crew that are constantly being improved, and some of that you've seen in the recent years that are becoming much more prevalent. However, all of these applications and these systems and technologies that are needed could benefit from wireless power, as the power is going to be distributed across these long distances, and they will certainly require grids of energy, as power will go from one point to another and traverses between these systems, where there's a fundamental shift from what is happening, what we had previously, where we launch from Earth and the satellites are stayed in orbit and then they slowly travel. So the speed of travel needs to be increased, as well as the complexity of the systems that are there. So all of that will be energy that required from that needs to be moved from point to point, and wireless power could be a great driver for that. This chart highlights a variety of wireless power modalities. So I have included the inductive and capacitive modality, just to highlight that it is not radiative. However, it is very important modality, and as you can see, it's pretty much the most popular modality right now with the electric cars, and the fact that it's highly efficient and it can transfer a lot of power in short distances very efficiently is very important, and that will certainly have its uses in space. However, on the radiative modes, the microwave, millimeter wave, and optical mode with lasers are the prevalent ones, with microwave being the most traditional mode of operation, where microwave sources that are highly scalable and efficient are used, and antennas are built to match them. The biggest issue with that is as the range increases, the power density is dropping because of the beam width being wider. And as a result, I mean, the advantage of that is that you don't need any pointing and tracking because the beam is everywhere and you can move within that. The issue would be the power density is lower, so the overall power will be lower. There may be also regulatory issues later on in space as communication and different protocols will come in, and you'll almost certainly at RF will be and microwave will be a very congested spectrum as it is on the Earth. On the millimeter wave side is the beam is narrower, much narrower than the microwave side, so that allows you to get to further range. The power density generated also from transmitters are much higher. There's a human safety limits for millimeter wave are much higher in power density. That allows humans to be present or close to the higher power density transfers. So that's actually a big pro for that. In the cons would be the complexity and the high tolerance parts that are required to build that, and some of that we're trying to alleviate by the new manufacturing technologies that are coming in. On the optical side, number one, I would say advantage for for space applications would be the fact that the optical side has a very collimated beam with the lasers, and they can traverse the long distances, especially with no atmospheric attenuation that would be present on the planet Earth. But obviously the advantages are there. The disadvantages could be the complexity of the systems that need to be built for generating that power. Although overall they're small, but tight alignments and requirements of temperature stability requirements and all of that could come into play for adding complexity to the system. So spaceborne wireless power transmission requirements might be different to what we have on Earth. One of the key elements of space hardware is size, weight, and power. So if you do have a system that operates very well on Earth and you have ground-to-ground power transmission that is highly successful, but the size of the transmitter is very large, that you're going to think about when you go to space. So since the weight is directly related to the payload weight, is directly related to the cost of the launch, and also the size is complexity, so you have to fold antennas and open antennas in space, and of course power-starved systems in space, and the whole point of this conversation. So the question would be, which is the modality that would best suit that specific space application? And obviously launch and survivability and reliability of the hardware is also key to that. Including some of the regulatory permissions that to come eventually. There will be regulatory permissions and interference issues that are going to come in as the space gets more populated. So those trade-off analysis will lead directly into the modalities, and some of the modalities are they all have pros and cons, and some are suited to applications that are specific to their advantages, such as, for example, millimeter wave could provide a very low swap based on the fact that the power densities and the transmitters are high and the receivers could be ultra lightweight. On the laser sources, on the optical side, you have the range that plays the key advantage here. So if you want to go long distances in space and not incur too much essentially loss, free space loss, effectively, your optical domain would be a good option to go at. On the microwave side also, there's key technologies that are being developed in space, especially with solar to ground to Earth effectively, radiation, power deliveries, technologies that are being developed, and that some of those technology can be leveraged for space to space. And what are those applications? Launch, space rocket launch would be one. So can wireless power transfer assist launching heavier rockets? Also point-to-point, space-to-space power feed, wireless power feed is yet another key element, and also trajectory change of the satellite. So as soon as you launch them, how fast can they get into position, where their final position? And those are the topics that we'll be talking about in the next few charts. This chart is directed energy in space rocket launch. So there's a plot on the left hand side where you see the launch cost and versus the number of years, and a whole variety of different launches have been highlighted. Each circle color depends of the country of launch. The size of the circle also highlights the payload size. And you can see a variety of the payload sizes are there, and as years have gone by, the cost is constant at $10,000 per kilogram, which is substantial for any desired mass to be shipped into space. You can see the interested area would be somewhere between the $100 to $1,000 per kilogram, where the demand would be, economic predictions would be. And then the question is how do we go from a $10,000 per kilogram to around 1,000? And you can argue that, you know, SpaceX is one path is by reusing the the launcher and relanding it and using it again. So that's one path to do that, but that doesn't really address the size of the payload as a function of the spacecraft itself. So one path was developed, the concept of it was developed in JPL and Caltech by Kevin Parkin. And the focus here is can you build a thermal thruster and use directed energy, being in this particular case W band and G band, and radiate a panel on the thruster while the fuel is inside of it. So effectively change the thermal balance of the fuel, so it burns hotter and generates more thrust. And this was experimentally also defined on a small experiment, and you can microwave energy or millimeter wave energy can be absorbed either by the fuel itself or an absorbing panel. And this is an interesting concept where the cost of generating the power is not very high on Earth, obviously, rather than space, and you could get an order of magnitude cost in the payload itself, the ratio of dollar per unit payload, and that was highlighted in that thesis, which is actually a very interesting talk. Go to the next chart, and you can see that if you had a heat exchange on the bottom left hand side and you have a hydrogen fuel coming in, the incoming beam is absorbed and the temperature of the hydrogen is increased. As a result, it burns harder and it gives you more thrust per unit area. And this was even tested at small scale, and it looked to be successful. So, and the option and to a large extent, you could build much easier. You can build the radiated transmitters on Earth a lot easier than you could in space. So, and these were at 95 gigahertz all the way up to 140 gigahertz, depending on the beam quality. And so the trade-off at the higher frequencies, you can the millimeter waves are absorbed by a lot of hydrocarbon fuels. And that was the concept, which actually had some merit to it. And if you look at this particular plot, shows you the what you're up against, which is effectively is the payload mass fraction. So how much payload is on the y-axis you can carry, and then the structural mass fraction, which effectively is the size of the rocket. Is the weight of the rocket. So you can see as the rocket weight increases, the amount of payload decreases, because you have only a certain amount of thrust that you can throw at this. And there are different technologies that are highlighted here, between obviously chemical and non-chemical and air breathing technologies. And the whole concept here is can the wireless power change this paradigm? You're going to need more thrust, and can directed energy allow you to do that? And the answer is yes, you can certainly do that, but of course it allows you to build more facilities on Earth, which could be cheaper and allow you to launch a lot faster, for example. So the other thing that we should look at is space-to-space power transfer. Even smaller amount of power is quite important. So having for example, space station here, you can see feeding in microsatellites, that with just 100 watts of power remotely, it would be pretty impressive, and it will allow these microsats to perform a variety of tasks that will otherwise won't be able to, because they'll be power starved. Because remember, the power comes from their solar panels. They're small, so the solar panels are small, and also they have to wait for charging to happen. But if you have directed energy and you have a lot of power coming in quickly, they can perform a variety of tasks that otherwise might not be the key. However, size, weight, and power is crucially important. If you reduce the solar panels, you can then add more rectangular capability maybe, and then question is what is that trade-off? Obviously lasers are a key aspect, so that could be that you could keep the solar panels and radiate with lasers and pick up more power from that, or replace them with rectangles. But in any case, it is an added power, and it is a very useful technique, especially if we have these waypoints with these stations, and then you have these grids of microsatellites close to them. So that's ideal for power, wireless power. The other one that is actually kind of interesting, this is kind of a little harder, but it does actually have a major effect for satellite launches. There's this geocentric orbit transfer. So if you look at the picture on the right hand side, you see the Earth. So launch happens from the Earth, and then the satellite sits in this transfer orbit, and it sits in the transfer orbit and slightly glides up. So the transfer orbit is the LEO, it goes up to LEO, and then slowly but surely it goes across that transfer orbit and gets into the geo orbit, and then eventually it partially deploys and then fully deploys, and then it's used. Now when you look at the time spent on doing that, the plot of the data that you can see is if you have the transfer time in days on the y-axis before it gets to geo, versus the kind of the payload, the maximum received power, amount of power that you need to kind of allow the satellite to have. So the higher you can see, the more power that the satellite has, the faster it can get into the geo orbit, which is kind of interesting because this is a power starved system. So if you don't have a lot of power, it's going to take you a long time to get there. So the way you would do it is by reducing your satellite mass, so payload goes down. Now if you have the worst case is if you have a lot of payload and you don't have a lot of power, and then it will take you 700 days, to get there, for example. But then so the question here is, can you wirelessly assist that and wirelessly power that independently, where you launch into this transfer orbit and you know where the waypoints are, and you assist these satellites to get pushed into orbit by radiating the power directly to them. If you look at what does it take to do so, so here's the power requirements versus power duration. So effectively the plots are joules, that's a 1 gigajoule and 1 terajoules. So the launch, for example, that we talked about, it sits there at somewhere in the region of about 100 megawatts, but it only needs 5 minutes. So it's not as bad. So especially if that's on the ground, it's completely doable. On the orbital change now, depending on what we want to do, you can essentially have a variety of different dots you can see on the terajoule kind of platform, up to 100 megawatt range, depending on what you're trying to do and where you want to go. But it does take longer time to do so. Interplanetary and interstellar, which is even higher power, it takes a lot more hours and a lot more power. So question is, if you do have sources that generate power in space and you can radiate that power wirelessly, you could assist in launch, in orbital change. So you can not only launch quicker, you can make the satellite go into orbit quicker. At the same time, you can work across the interplanetary and interstellar even concepts that you can move spacecraft in different locations with higher and higher power. But you can see for example, the interstellar of 100 terawatts. I mean, we're talking some serious power that will require a completely different paradigm shift. It can be radiated. Now the question is what do we have as far as sources? So this one was what I did is I put the kind of effective range versus effective power of these sources that are available. So satellite RF transmitters for comm links to ground, space to ground, they sit up at geo level, and obviously their effective range is really high, and the issue with them is that they're low power because they're radiating back in on Earth and they have to follow the IEEE spectrum, which is very, very low power. So what they have is they have the transmitters, but they have very sensitive receivers that allow them to communicate on the other side. Space station has 27,000 square feet of solar panels, which allows it to have some 100 kilowatts of power on board. And then you have the ground-based systems, which are the high-energy lasers, which are now pushing up, up to 100 kilowatts and beyond maybe. And then you have the active denial systems, which are kind of a directed energy, non-lethal weapons. And these can be built up to, obviously 100 kilowatts is already built, and 7 kilowatts. But possibilities are that you could get up to multiple megawatts with these systems if needed. On the EMP, which is electromagnetic pulse power, for a variety of application spaces, you can get gigawatts of power, but obviously it's going to be very short timelines, microseconds or whatever. It's a pulse that comes in. Now these are all these units were built for different applications, but the question is, if you had to build a system that would enable you to for long periods of time to radiate that kind of power, that's a completely different design that you require, and the power source that feeds that needs to be carefully thought about. So it could be multimodality power source, such as a nuclear to RF or nuclear to laser, or a variety of, and that needs to be carefully thought about, size, weight, and power. So as far as the technologies are concerned, what do we have that could be used in space? And one of the key aspects of work that we've done on the millimeter wave, you can see here, it's our transmitter, which is about 60 centimeters by 60 centimeter aperture, 7 kilowatt transmitter, a W band frequency, and it's a completely scalable structure. We're using gallium nitride power amplifiers at 92 gigahertz, and then we'll build these 7-watt submodules. Those submodules get into the module of 100 watts, and those 100-watt modules go into the panel and generate 7 kilowatts of power. It's very tactical. I mean, systems such as this could be used for directing hundreds of watts into a variety of, for example, microsats as needed. And this is very, very compact, very low swap, concept, and we are also looking at even lower swap concepts that could allow these units to operate. And then what is actually in space? So if you look at communication satellites, that they have a huge amount of RF power. So these are L-band, S-band. You can see the traveling wave tube amplifiers and the solid-state power amplifiers, and the output power is not very high output power, because as I mentioned, is more focused on radiating the power on Earth. So with the power density is already designated to be low, so they cannot be very high power. However, these sources are available, so they could, and they have flown in space, so technology can be built and put in space, and they are in reasonable cost. They're not too very expensive. And then the solid state is coming up really fast. Obviously, a lot of them are low frequency for longer range, but we could certainly accommodate larger power densities, as well as more compact systems. Now, one of the key aspects of if you did have that capability in space, what would it look like? So one of the things that I was running kind of a system analysis on the wireless power transfer, and this was done with let's say if you had a transmitter that was 100 kilowatts, and it was and you had so you were running various ranges. If the transmitter antenna was 2.5 meters, which is not too bad, it's similar to comm antennas in space, communication and satellites. And what if you had a receiver antenna was very large? So let's say 250 meters sail, and you can see a picture of that from NASA that could highlight something that could be built. It's essentially a foldable antenna that deploys itself, and because you're in space, you could slowly deploy such a thing and then build a very, very large antenna. And the reason you want to build a large antenna, because you want to capture all that radiated power at the distance. And I ran the numbers at 35 gigahertz, 94 gigahertz, and I pushed it up to 220 gigahertz. And you can see the plot on the right hand side, where the range is 100 kilometers, 300, 500, 700, and 900 kilometers, which is not exactly a lot of, the ranges, it could be even higher. But you can see almost 220 gigahertz, because there is no atmospheric losses at 220 gigahertz. At 94 gigahertz or 220 gigahertz that are appreciable. The beam width, it gets narrower and narrower as you go up in the sub-millimeter wave range. So as a result, you can capture more and more of that power using your 250 meter sail. And then at 94 gigahertz, you have a lot more mature technologies, obviously, because building a 220 gigahertz source in space at this kind of levels would be harder. But at 94, we already have 100 kilowatt sources that are available. So those are kind of some of the trade-offs. And then, of course, 35 gigahertz, the beam width is wider, so you're going to need a bigger sail to capture more to climb back up. But nevertheless, it shows some reasonable amounts of power, 10 kilowatt range or higher, that you could, a kilowatt or 10 kilowatt range, that would be very useful within those ranges that you. Now, what are the receiving technologies? So this is kind of a rectangular performance of some of the charts that some of the papers that I've put together. And this is kind of, I presented this before, where you can see the efficiency as a function of frequency. So, majority of the rectangles are designed or at 2.4 or 5.8 gigahertz, with a few at 35 and some at 94. And you can see the efficiency slopes down and goes down as a function of frequency, which is effectively the 1/f squared loss factor of devices and circuits. So loss mechanisms go up as you go up in frequency, and that's to be expected. If you just scale the same topologies through it. And then the power, input power of milliwatts per centimeter square is shown in orange across. And it's kind of surprising that literally the power is kind of flat across the frequency for a lot of them. And the reason mainly is because the same technology applies, so the power density remains the same. But the key, what we try to do is to, at about 94 gigahertz, is to push the power density and also efficiency up. So to start to develop rectenna technologies that are on the top right hand side of the chart. And then so one thing is to build the rectenna circuits, the antenna arrays, and the input filter rectifier, and I'm sure we all know about that. That could be very compact. It could be thin film. It could be, we could easily incorporate that into the sale and build it with the technology, manufacturing technology that are available. The question would be, is the more on the power management and storage. Let's say you did get all that power. What would you do with it? Where would the power go? So that needs to be a lot more thought about, because those kind of technologies to hold power for large amount of power, it's not a very compact way, because batteries are heavy. You could work on supercaps, but the supercaps have their own issues, as you can see on the power density versus energy density. So you could start to think about, if I did have a wireless power, is not going to be the same as the normal power that you would have in your satellite. So it is power and signal on demand. So as soon as you get the power, you're up and running, and you do what you need to do, and when the power is off, you stop working it with minimal amount of battery for backup systems. That could be one path to do that. That reduces the power management and conditioning, and certainly the storage. So on the solar photovoltaic cells, you can see the multi-junction photocells that could be built, and some record performances have been shown, where you have the solar effectively the solar bandwidths with gallium indium phosphide and gallium indium arsenide and germanium for a variety of different sources, and so you could essentially have laser sources that would be also absorbed efficiently. So technologies exist for that. Obviously they have to be lower cost and space proof, which some of them are these days, and considering that this is done with epitaxially, they could you could envisage that this could be a reasonably low level of effort, hopefully, to make them space qualified. At the same time, you can take full advantage of what is happening on the solar PV system, and what all the peripherals that go around it as to its conditioning, is controllers and isolators, and the way they all the solar panels are connected together to give you the highest feasibility that you could take. So some of that needs to be looked into. So in conclusion, the space applications provide opportunities for wireless power transfer, especially with the exploration to Mars. The game is changing, where we need to have waypoints in space with production, with grids, with all sorts of capabilities that we could even have space launches. Within having more material sent up into space is also crucial. SpaceX is one company's technique of using the launcher. The other path is to make the launch much easier and provide an increased payload per launch, and that is definitely wireless power could help in that. Orbital change is another, so just in case, once you have these systems up into space, we have to get them into the right points faster, so assisting their path into the journey they have, whether it's the geo, whether it's further than that, into their waypoints, and wireless power could help in that. And also, of course, the microgrid version of network of wireless power between these installations will take a large effort in making a communication between a variety of different units easier, and also more sustainable, maybe even more cost effective. In general, the technologies to use millimeter wave and optical side lasers provide an excellent capability for space. And question would be is the swap capabilities that either the millimeter wave or optical systems have. And a lot of those are being tried right now in space, and some of that data would be very useful to highlight what would be the next technologies going forward. As I mentioned, microwave, RF and microwave is definitely a key capability that is not to be ignored. As long as we have large apertures, they would do very, very well in space as well. So thank you very much.